Good morning to you three. We'll see. Okay, so morning. We're gonna keep going with functions today. We did 2.3, 2.4, 2.5, 2.6 last day. That was a lot, but there wasn't a lot of new material in there. The only thing was kind of 2.6 where we talk about stretching and shrinking horizontally, vertically, shifting, and that kind of stuff. So just as a quick review from last day, we were talking about functions. And I guess I should not have colon. So functions, we talked about increasing and decreasing functions. What was nice about increasing and decreasing functions is that we were given the just the mathematical definition of increasing and decreasing, but what's nice is we actually know what an increasing function looks like, right? It's kind of going like this, or it can be straight if you wanted to, right? Where if a is less than b and you put them into the function, then f of a is going to be less than f of b. And so we were able to make that connection between the mathematical definition and what we already know about an increasing and decreasing function. So we talked about increasing / decreasing functions. We use that, the increasing and decreasing, to define the local maximums and minimums, right? So if a function goes from increasing and then at some point it switches to be a decreasing function, well, that point is a maximum, as opposed to if you've got a decreasing function and then at some point it switches to be an increasing function, then you've got a local minimum. So we talked about local maximums and minimums. We talked about the average rate of change of a function. The average rate of change, which we said was f of b minus f of a over b minus a, right? Which is actually also the net change over b minus a. Right, we've already seen the net change in earlier sections, so I think it was even in 2.1, right? So the net change is f of b minus f of a, and then if we take into account how much of the x-axis we've taken up, then we've got the average rate of change, right? And then we applied that to linear functions, and we kind of went into linear functions. Linear functions have the slope equals to the average rate of change, which is nice because then we'll always know that the average rate of change of a linear function is just the slope, and therefore it's constant, right? And which makes sense. If you've got a straight line, then the average rate of change is just going to be constant. So that's pretty much what we said in 2.5. And then we got into transformations of functions. And of course, we spent a fair chunk of time on that. And so we can't really review it because it would just be last day's class all over again. But we can have vertical shifting, horizontal shifting, right? We can have vertical stretching, vertical shrinking, horizontal stretching, horizontal shrinking. We can have reflections around the x-axis, around the y-axis, right? All these things are all possible, and we need to be able to break down a function from its core function and see, okay, what changes have been made, and then we should be able to sketch that graph. We also talked about even and odd functions. So even functions are symmetric around the y-axis, whereas odd functions are symmetric around the origin, but we also talked about even and odd functions, right? If the highest power is even, you have an even function, and if the highest power is odd, you have an odd function, power of x. Okay. So today it's going to be a lot of algebra, a lot of just straight math, plug and chug, but it's going to be in a different way than what we've seen before. So unless you've seen algebra functions before, then that's great. But let's see here. I have the old version here, but that's okay. So combining functions. Okay. So combining functions are, if we have two functions f and g, then those are two individual functions, but we can combine those functions to make new different functions, right? And so we can use two functions to make new functions using function algebra. Or algebra of functions, I guess I should call it. Just to match the blurb. Okay, so we've got things like f plus g. We can find f plus g, f minus g, f times g, f over g, as well as if A is the domain of f and B is the domain of g, then we can talk about the domains of all these things. Notice that they're always the same until you've got g of x in the divisor. Then we've got the added condition, right? A and B is the domain still, but g of x can't be 0, right? So we've got that added condition. Okay, well, we can't divide by 0, so make sure that doesn't happen. But otherwise, the algebra of functions behaves exactly the same way you want it to intuitively. So f plus g of x is just f of x plus g of x. F minus g of x. So notice that the new function name is f plus g or f minus g, f times g, f over g, and then of x, right? But what we can do is we can just write it out as f of x plus g of x, f of x minus g of x, f of x times g of x, f of x over g of x, right? So nothing too crazy, but notice that we will, once we simplify these things, we will have new functions that we can work with. And so if we're talking about the domain A and B, right, this is read as A and B, is the overlap of A and B, right? And so here, overlap of the domain of F and the domain of G. Right, so if we have to deal with the domains, since I'm looking at the same domain for all of these with the added condition of g of x can't be 0, it might be a good idea to just find what is this A and B. So what's this overlap of the domains? And then you just know what the domain is for each of these. So that's where I'm going to start in my examples. Is I'm first going to find the domain, and then I'm going to go ahead and figure out what these are, because then I can just say, hey, the domain is exactly what we found up above. So, oops. Okay. So we're asked to find f plus g, f minus g, f times g, f over g, and their domains. So let's start with something nice and slow. Let's do 10, right? And so 10, just writing out what the functions are, f of x is 3 minus x squared, and g of x is x squared minus 4. Okay, so each of these is going to have a domain, right? As soon as we have a polynomial has the domain of all real numbers, right? And so the only time that we have restrictions on the domains is if we see something like a square root or x in the denominator of division, right? Because we can't divide by 0, we can't take the square root of a negative number. And so looking at all of these, here's a little square root. So we would have a restriction on the domain here, right? X can't be less than 0. Here, there's no restrictions until we hit the square roots again and the division. Then we would have some restrictions on these domains. But how we're going to write these is if we let A be the domain of f of x, then A is the set of x such that x is in the set of real numbers. Right? Using our fancy set builder notation, or if you wanted to, x is in the set of reals. Right? In interval notation, from negative infinity to positive infinity, round brackets around both. Just depends on how we have to enter our answers. But for now, I'm just going to write them like this. So, and then B is going to be the domain of g of x. So B is the set of x's such that x is in the set of real numbers because there are no restrictions on what x can be here. All right, there's no square roots, there's no division, so we're good. So then A and B is the overlap of A and B, but if A can go from negative infinity to positive infinity, and B can go from negative infinity to positive infinity, then it's like the witching hour for my printer. I feel like it's always acting up just during our class. Anyways, doesn't matter. If B goes from negative infinity to positive infinity, the overlap of those two would be from negative infinity to positive infinity. And so we have the set of x's such that x is in a set of real numbers. Okay, so all right, so we have our domain, right? And then what we're gonna do is once we've done the division, f over g, then I'll find the domain of that specific one, right? Because I can't divide by g of x equal to 0. So values that make this 0 would have to be pulled out of the domain. So now we can go ahead and we can actually find these f plus g, these new functions, f plus g, f minus g, f times g, f over g. And so we have f plus g of x is the same as f of x plus g of x. Sometimes I'll just skip straight to writing it like this. I don't really like this notation. It doesn't tell me what to do, whereas this one tells me what to do. They're equivalent, so we can use them interchangeably. But technically what we're finding is the function f plus g of x. So f of x plus g of x, f of x is 3 minus x squared. So 3 minus x squared, I'm going to put it in brackets because they're all from f of x, especially if I have g of x and there's negatives involved, and I don't want to get too messy here. g of x is x squared minus 4. So now I can simplify this by getting rid of these brackets, so I get 3 minus x squared plus x squared minus 4. Minus x squared plus x squared, those are going to go away. 3 minus 4 puts me at -1. So it's not a function of x at all, right? But that's okay. This is f plus g of x. And then the domain is the set of x's, or whoops, I already did it. Defined it as a and b, so what I'll just do is a and b. Okay, there. Maybe I should make that look more curved. There. What if we do f minus g of x? So same deal, just subtracting f of x minus g of x. So f minus g of x is f of x minus g of x. Same thing, the only thing that I'm changing here is the minus, which has to get pulled in here, right? And so what I get is I have 3 minus x squared minus x squared minus 4, which when I expand this out, 3 minus x squared minus x squared plus 4. So 3 plus 4 makes 7 minus 2x squared. Often I like to write the highest power of x first and then decreasing powers of x. So this becomes -2x squared plus 7. So now I've got an x in here, so that's nice. It's not necessary, but it's pretty common that you end up with an x in there. The domain, again, is a and b, just by definition. F times g of x is f of x times g of x. So now I'm going to get a slightly larger function, right? So I've got 3 minus x squared times x squared minus 4. If I expand this out, you can FOIL if you want. 3 times x squared is 3x squared minus 3 times 4 minus 12 minus x to the 4th plus 4x squared. So again, I'm gonna, after I combine my like terms here, so 3x squared plus 4x squared, but I'm also gonna rewrite these in decreasing powers of x. So I get negative x to the 4th plus 7x squared minus 12. And if you're pulling a fast one like I just did here, then just make sure that you're double checking your work, right? So 3x squared plus 4x squared is 7x squared minus x to the 4th minus 12. Okay, looks like they're all there. And the domain again is a and b. Yeah. The last one, f over g of x is just f of x over g of x. So we're going to solve it and then we're going to figure out what the domain is afterwards. Remember, the domain is going to be a and b, so the overlap, which is in this case all real numbers, but taking away any values of x that make g of x equal to 0, right? Because I can't divide by 0. So f of x is 3 minus x squared over g of x, which is x squared minus 4. So can I simplify this? I guess. x squared minus 4 I can, but it doesn't really cancel out. So I'm just going to leave the function here, right? If there's nothing that jumps out at you, then you can probably just leave it. But there's nothing I can cancel. I don't think I can factor out to get a common factor, so I'm just going to leave it. So here, the domain, right, from the definition here, is all the x's in A and B such that g of x is not equal to 0. So we need to figure out where g of x is equal to 0 and pull those out. Domain in kind of words is A and B excluding values of x that make g of x equal to 0. So g of x is x squared minus 4, and we want to figure out where it's equal to 0, or if you prefer where it's not equal to 0, it doesn't matter, you're going to land on the same values. So this thing is equal to 0. From here, if you just kind of focus on x squared minus 4 equals 0, then you can add 4 to both sides, so you get x squared is 4. And then when you take the square root, remember you have to take the plus minus on both. So then you get x is plus minus the square root of 4. So x is plus minus 2. Which we can check. If x is 2, 2 squared minus 4 is 0, so that's a no-go. If x is negative 2, you get negative 2 squared, which is also 4, minus 4, which is also 0. Right? And so these x equals plus minus 2 have to get pulled out from the domain. So the domain, the new domain, is the set of x's such that x is in the set of reals and x is not equal to plus minus 2. So now, this is just one little added step, right? But now we've seen the algebra of functions just for these two very kind of basic situations, right? And so which one do I want to do? Let's do 13, right? Let's do one with the root, right? Just to see what's going on. Or maybe we should do 16. It's going to be harder. No, I like 13 because it's hard in its own way. Only because 16 they have the same domain, so it's kind of boring. This one we have different domains. Oh, sorry, my nose is so runny, I don't know. I feel like I say that every day though. 13, f of x, I've just got it on the side here. From my notes, 25 minus x squared, and then g of x is the root of x plus 3. So now we've got these square roots, which we have to make sure that we don't take the square root of a negative number, right? And so here, remember, we can't take the square root, oops, of a negative number. So just remembering that. So if I let A be the domain of F, then looking at this here, what I'm saying is that 25 minus x squared always has to be greater than or equal to 0. So then what I'm saying is that 25 minus x squared has to be greater than or equal to 0 because I can't take the square root of a negative number. Now it's pretty easy to see here that of course x squared can't be larger than 25, right? And so, but we can solve this. We can add x squared to both sides if you prefer, or you can subtract 25 from both sides, but then you're dividing by this negative, which is going to have to switch the signs. Either way, doesn't matter. 25 has to be greater than or equal to x squared. Okay. So once I take the square root of both sides, right, again, I'm going to have a plus minus root 25. Root 25 is just 5. So this becomes plus minus root 25 has to be greater than or equal to x squared. Fine, I get plus minus 5 has to be greater than or equal to x. And so on a number line, right, let's see here. If I've got negative 5 and I've got positive 5, x has to be less than positive 5, but greater than negative 5. And how does that translate? I just know that that's the truth. So I'm missing something here. I'm going to delete this. And this. I'm just going to do, because I know what it is. X has to be between negative 5 and 5, right? And you can check it. If you do negative 6 squared, that would be 25 minus 36, which is less than 0, so that's bad. As long as x is between negative 5 and 5, you're okay. Another way that you can check this is just graph this whole thing in Desmos just to see what it looks like to find the domain. So if we graph the square root of 25 minus x squared, what we get is we get this semicircle from negative 5, so x equals negative 5 to 5. So it makes sense what we're saying, that x has to be between negative 5 and 5. So okay. So the domain of f is that x is between negative 5 and 5. The domain of g is similar. It's a little bit easier. It's just that x plus 3 has to be greater than or equal to 0. What I'm going to do is I'm going to squeeze this onto the same page. And let b be the domain of g. So then g of x is x plus root of x plus 3. So x plus 3 has to be greater than or equal to 0, which means x has to be greater than or equal to negative 3. So now, remember, the domain of both of these, right, is the combination of a and b. So we have to find the overlap. Okay, so I like to use a number line here. Whee! I've got some key players. I've got negative 3, negative 5, 5, and then I'll put 0 on there just for reference. 0, 5, negative 5, negative 3. So if if A is the domain of F, I'm going to plot those. Notice that it's including the endpoints. So I'm going to have closed dots here at 5 and -5. And A is going to be everything in between. Whereas the domain of G is X is greater than or equal to -3. And so here at -3, I've got a closed dot because it can be equal to -3, and then it just keeps going and going, which we can confirm if we do the root of x plus 3 in Desmos, right? If we can even put them on the same graph here. The root of x plus 3 starts here at x equals -3, and then all the values greater than -3. So if we go and we find that this is B, right? A and B is the overlap of these two. So that's only between -3 and 5, right? That's the overlap of these two. And so notice that these two circles are closed. So I'll pick a different color here. Closed at -3 to 5. So A and B is the orange one, the overlap. Oh, I guess I should color code these. There. So then A and B is the set of x's such that x is between two numbers less than or equal to or greater than or equal to -3 and less than or equal to +5. So that's going to be our domain for the first 3 combinations. And then for the last combination, we're saying g of x can't be equal to 0. So the only thing that changes is that, well, it's equal to 0 if x is equal to -3. So I'm just going to pull that option out and just have x has to be greater than -3. But we'll deal with that when we get there. So f plus g of x is the same as f of x plus g of x. I've got the root of 25 minus x squared plus the root of x plus 3. Now, I'm not seeing a simple way to simplify this. I cannot put them under the same square root. I can only do that if I'm multiplying or dividing, right? Because those are those exponent laws that we talked about. So I can only combine them if I'm multiplying or dividing. So looks like I'm stuck here, right? And that's okay. I'll just leave it at that. And the domain here, the domain is A and B, which is the one that we just found here. Okay. What we can do is we can graph this just to see what it would look like, and I'm really hoping that the domain is going to be from -3 to 5, otherwise I'm hooked. I'll change this to plus the square root of x plus 3. Looks good, right? So here, -3 to 5. Phew. Weird looking graph, right? But that's okay. So you can always graph to make sure that things are working the way you think it will. What if we do f minus g of x? Is f of x minus g of x? Well, it's going to look a lot like this, except we're going to have subtraction in here. So it's going to be the root of 25 minus x squared minus the root of x plus 3. Now, again, there's not much I can do to simplify. I'll make this actually look like a 3. There's not much I can do to simplify this because I'm adding or subtracting, so I can't combine that root. So the domain is A and B again. Notice that this is a difference of squares, so we could factor this. I just don't see any benefit right now, or even later. If I do f times g of x, well, that's f of x times g of x. Now I've got the square root of 25 minus x squared times the square root of x plus 3. Finally, I'm multiplying these square roots, which means that I can combine them under the same square root if I want to. Because we can rewrite the square roots as 25 minus x squared to the power of 1/2 times x plus 3 to the power of 1/2, and then by the exponent laws, we can combine these. So this becomes the square root of 25 minus x squared times x plus 3. We can expand this if we want to. Let's do it. Let's see if we can get anything here. Square root of 25x plus 75 minus x to the 3 minus 3x squared. Again, there's nothing I can simplify, but I can rewrite this with my highest power of x first and then decreasing powers of x. So I'm going to do that. Negative x to the 3 minus 3x squared plus 25x plus 75. Just remember to make a note in my notes here. And the domain here, of course, again, is that A and B. So now let's do f over g of x. So let's find the function first, and then we'll figure out the domain, which we already talked about, so it's not going to be that bad. So f of x, oops, almost got right to it, and that's okay. If you want to just get right to it, that's okay. F of x over g of x is the root of 25 minus x squared over the root of x plus 3. I can combine this under one square root. If I was able to factor this out into something that canceled, that might be tempting. I don't see anything though, so I'm just going to leave it as is. But you could put them all under the same square root if you want to. So 25 minus x squared over x plus 3. Now the domain is A and B excluding values where g of x is equal to 0. So g of x is equal to 0. So g of x is the root of x plus 3. G of x is equal to 0 when the root of x plus 3 is equal to 0. The root of x plus 3 is equal to 0 when x plus 3 is equal to 0. So that's where x plus 3 equals 0. So that's at x equals negative 3. And so the domain becomes the set of x's such that x is just greater than negative 3, right? So no longer including that negative 3 and less than 5. Good. So that's the only kind of change up with the domain when we're dividing these functions is we have to make sure that g of x is not equal to 0. All right, good. So there's some more domain problems here. You'll see I posted the solutions to all the chapter 2 notes on Moodle, so you've got those. So you can go through and find these domains. These are going to be a little bit trickier, right? But what I want to talk about is the composition of functions. Composition of functions are pretty fun. We're just kind of stuffing functions inside other functions. And again, we're just really making new functions. So composition of functions. And I'll also talk about the domain. But I'm not going to worry too much about the domain. We talk about the domain so much in other aspects, so we'll talk about it. But because it can be kind of tricky sometimes, I want you to focus on the function composition. So the composition of two functions, f and g, we write as f and then a little hollow circle g. So this is the composition. So f composed with g. So f, little circle g, we read as f composed with g, right? Or more simply, it's where we plug g of x into f of x. And so f composed with g, right? Or usually I just write that or read this as kind of. Pretty improper. It is technically f composed with g, right? So what I say is improperly, we can say f of g. It works, right? Because it's f of g of x, right? But technically what we should be saying is f composed with g, but if you read it as f of g, it totally works. It totally makes sense because it's just f of g of x, so you're plugging that g of x into that f of x. So, right, f composed with g, and then usually we write it like this, of x, which has the same kind of layout as here, right? Is f of g of x. Often I'll just skip straight to this notation, right? And we can make f composed with f, so that's f of x, right, where we stuff in f of x into itself, right? So just to make a note, the domain of f composed with g, so f of g, is the set of all x in the domain of g as long as g of x is in the domain of f. So, so it's defined, or the domain is the domain of g of x as well as f of g of x. Okay. So that's a little bit trickier than what I want you to focus on right now. Let's do some of these compositions. Okay, so what we're asked to find, and I'm just gonna lightly kind of cross this out for now. If you're working on these problems on your own, then definitely try to find the domains and check against the solutions that I've posted, right? So we're gonna leave them out for now because I don't wanna cloud your brains, but definitely give it a try, right? See if you can do it. But like I said, I don't wanna get too messy here. Let's do 48. 48 to start. And so I'm given f is 6x minus 5, and I'm given g, which is x over 2. I'm going to find f composed with g, g composed with f composed with f, and g composed with g, right? And so we're going to get all these different functions out of this. So 48 says we have f of x is 6x minus 5, and g of x is x over 2. Just as as a quick refresher, right? The domain of f of x is any real number. I can put in any value for x and it'll still work. Even for g of x, it's any real numbers because the x is in the numerator, right? Any number can be divided by 2, so everything goes, right? So I've got a set of real numbers and a set of real numbers. But like I said, we're not gonna focus on that. F composed with g of x is the same as f of g of x. Now, sometimes later, once we've done a few of these, what I might do is I might just jump right in and substitute g of x into f of x right away and skip this step. But for now, what I'm going to do is I'm going to have 6g of x minus 5, right? Wherever I see an x in f of x, I'm going to replace it with g of x, regardless of what g of x is for now. Then my next step is I'm going to replace all my g of x's with x over 2. So I get 6 times x over 2 and then minus 5. Luckily this cancels, right? 6 divided by 2 is 3, so I don't have to find a common denominator to combine these. I just get 3x minus 5. And that's my new function, f of g of x. F composed with g of x, right? We can do the same thing, g composed with f of x is g of f of x. G is x over 2, so we have f of x over 2, where f of x is actually 6x minus 5, so now I'm going to make that substitution. 6x minus 5 divided by 2. Both of these terms are being divided by 2, so we have to be really careful, right? Because now I get 6x divided by 2 minus 5 over 2, which is 3x minus 5 over 2. Okay. How about f composed with f of x? So a lot of these, it's just straight algebra, right? We're just doing math, 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 math to simplify, to combine these things. So it's not really that terrible. It's just sometimes they can get really bulky, really big. So f of x is f of x, where f of x was 6x minus 5. So I get 6 f of x minus 5. F of x is 6x minus 5, and then minus 5. I can expand this and simplify, so I get 36x minus 30 minus 5. Did I copy? Yeah. So I get 36x minus 35. How about g of x? G of x is x over 2. Okay, so I get g of x over 2, which is x over 2 over 2. I've got a fraction over a fraction essentially, right? 2 over 1. So I'm going to flip the denominator and multiply. So I get x over 2 times 1 over 2, x over 4 is my new function. Okay. Good. Let's do one with a fraction in it, just to practice some of our fraction work. Right, let's do 55 here. Or you know what? Let's do 57. That's a hard one. Why is it hard? Well, I've got x in the numerator, I've got x in the denominator, and then I've got another fraction 1 over x. So this one's definitely difficult, so let's do this one together. Let's talk about even though we're not dealing with the domain, right? The domain of f of x is x can't be -1. If x is -1, I have -1 plus 1 makes 0. I'm dividing by 0, not allowed. Here, so x can't be -1, and in g of x, x can't be 0, right? But because I'm in f composed with g, I'm plugging in g of x into f of x, right? What I'm saying is 1 over x can't be -1, right? Because now I'm plugging in this g of x in here. So you can see how this gets a little bit tricky, and that's why I'm just focusing on the compositions, but it's good to keep in mind. Okay, so if we start with f composed with g of x, that's f of g of x. F is x over x plus 1. G is 1 over x. So here, I'm going to have g of x divided by g of x plus 1. Now, I'm going to replace g of x with 1 over x. So I get 1 over x over 1 over x plus 1. Before I can combine these, right, I need a common denominator. And so what I'm going to do up here is I'm going to multiply by x over x to force that common denominator. And I am moving quite a bit faster than we have been doing, right? But we've done all these problems already. So they should be feeling pretty good by now. So 1 over x over 1 plus x over x. Now I've got a fraction over a fraction. Even though it looks nasty, I can flip and multiply. And so I get 1 over x times, and then 1 over x, 1 plus x over x becomes x over 1 plus x. X over 1 plus x. I'm going to put brackets around the 1 plus x to signify that those hang together. What's nice is this x over x is going to cancel out. Boop, boop. So finally, I just have 1 over 1 plus x is my f composed with g of x is 1 over 1 plus x. Okay. How about, let's do g composed with f of x. I'm going to try to keep it on this same line. Otherwise, it becomes just pages upon pages. Too much scrolling for me. So that's g of f of x, although I should have thought of it before I took up so much room here. Maybe I can make myself a little bit more room. There, that's good enough. G of f of x is going to be 1 over f of x. F of x can go in 1 divided by x over x plus 1, making sure you treat it as one thing. I've already got a fraction over a fraction, so this one's going to move a little bit faster. And so I've got is 1 over 1 times x plus 1 over x. So this just becomes x plus 1 over x. What if I wanted to do, or now I want to do f composed with f? F composed with f is just f of x. F of x is x over x plus 1. So now I'm going to have f of x over f of x plus 1. Now I've got x over x plus 1 divided by x over x plus 1 plus 1. Careful here, you have to find that common denominator. And so we're going to do that in the next step here before I can flip and multiply my fraction over a fraction. So I have x over x plus 1 divided by x over x plus 1 times x plus 1 over x plus 1, forcing that common denominator of technically 1 times x plus 1. So I get x over x plus 1 is x plus 1 over x plus 1. Okay. X plus 1 is 2x plus 1. And when I flip and multiply, a lot of this stuff is going to cancel out. So I get x over x plus 1 times x plus 1 over 2x plus 1. Making sure that I keep these two on their own. X plus 1 divided by x plus 1 just goes to 1. So we get x over 2x plus 1. And then there's nothing else that we can cancel because we would have to have an x over here in this term as well in order to pull out that common factor. So now, what if we want to do g composed with g of x? That's g of x. G of x, 1 over x. So 1 over g of x, which is 1 over x. 1 is just 1 over 1, 1 over 1 over 1 over x. Flip and multiply. And so I get 1 over 1 times x over 1. Wow, that just leaves me at x. Way easier than f composed with f, g composed with g. But it just depends on what the functions are that you're dealing with, right? So, nice. All right, so you can go ahead and do the rest of those, definitely for practice. There's also things like it might be useful to be able to break down a bigger function into a function composition. So if we have something like this, right, express the function in the form f composed with g. So now we have these composed functions and we want to see, and there are lots of different options, some more obvious than others though, right? So if we look at something like 65 says g of x, capital G of x, is x squared over x squared plus 4. If capital G of x is f of g of x, right, that's what we're trying to force here. Let f of x, so f of x is the outside function, and then g of x has been inserted into it. So if I let f of x just be x over x plus 4, right? X over x plus 4, and let g of x be x squared, then f composed with g of x is x squared over x squared plus 4, which is exactly what I wanted. So this is an option. There are other options, but this is the most obvious. Even something like, what if we had 66? I would probably resist the temptation of just letting g of x be x, right? We want to challenge ourselves a little bit. And also that doesn't really help me much later on in math when I have to do substitutions. So 1 over x plus 3, if capital G of x is f composed with g of x, we can let f of x, well, we can let f of x be 1 over x, and let g of x be x plus 3. That's kind of a clever way to put this thing together, right? X plus 3 is getting put in here. Instead of just saying, okay, well, I'm going to let g of x be x and f of x be 1 over x plus 3. It works, but it's not very clever. Right? So this is the most obvious substitution that we could do. If you go to your notes, you'll see that there's some other stuff labeled optional. If we kind of zoom in, now we're looking at 3 functions, so not just the composition of 2 functions, but 3 functions, which means we're just stuffing functions inside each other, right? H goes into G, G of H goes into F, right? That kind of thing. And so here, this first one's not so bad, right? X minus 1 goes into the root of X, so you have the root of X minus 1, which goes into X minus 1, so you have the root of X minus 1, all minus 1. Not too bad, but once you get into something weird like this, ugh, no thank you, right? It's optional. Give it a try, but I'm not going to test you on it. Same thing here. We could write a big function as a function of a composition of 3 functions. Same thing that we were just doing up here, right? But now we're talking about 3 functions. So I'm leaving that as optional for you guys to try if you want to. But we are going to get into one-to-one functions and their inverses. This is the last section in chapter 2. And so the last section on pure functions, we're going to keep dealing with functions throughout the course, of course, but this is kind of a big chapter, or a big section of this chapter. So I'll put it on a new page, start fresh here. So what's going to happen is we're first going to talk about one-to-one functions. One-to-one functions are if you have the same output level, so the same value of y, what it means to be one-to-one is that you can't have 2 different values of x that give you the same output. So if you're thinking about x squared, for example, it is not one-to-one because x equals -2 or x equals -2 gives you the same value as x equals 2, right? They both give you 4. So that by definition is not one-to-one. Graphic, or kind of in a little cartoony here, a function that's one-to-one means that each input gives 1 output, and each output comes from a single input, right? So here, this is not one-to-one because 2 maps to 4 and 3 maps to 4 by some mechanism, right? So this is not one-to-one. So what it's saying is that if the output of, so let's just read it. A function with domain A is called a one-to-one function if no 2 elements of A have the same image. That is, f of x1 does not equal f of x2 as long as x1 is not equal to x2. So one-to-one functions, we need one-to-one functions in order to find the inverse of a function. So we're working up towards finding the inverse of a function. But first we need to determine if a function is one-to-one, because it only has an inverse if it is one-to-one. So I'll put in a pink note here. We need to be able to show if a function is one-to-one or not because only one-to-one functions have an inverse. So we need to first be able to show that something's one-to-one, and then we'll be able to find the inverse. So that's what we're getting to later today. But in order to prove that something is one-to-one, right, we need some sort of way to show that. So we can prove mathematically that a function is one-to-one one-to-one by setting f of a equal to f of b and simplifying if it simplifies to a equals b, the function is one-to-one. So if it simplifies to a equals b, the function is one-to-one. So that's mathematically. As a rule, any even powers are not going to be one-to-one. And so I'll do it in a different color. Even powers are not one-to-one unless the domain has been restricted. Unless the domain has been restricted. So for example, if we've got something like x squared here, that's an even power, or maybe I'll put this up here, versus x to the power of 3, something like this. Okay. If we have A and B, right? What we're finding is that they have the same output, right? That by definition is not one-to-one. So here, f of A is equal to f of B. So not one-to-one. What I mean by unless the domain has been restricted. So unless it says something like, we'll only consider values between 0 and infinity. Well, all of a sudden you're blocking out this whole section and all of a sudden it's one-to-one because you only have one output value for each input value, right? Or rather, there's only one instance of each output, right? Whereas here, x to the power of 3, well, there's no two values of x that give you the same output value. So it is one-to-one. Oops. One-to-one. So just as a quick check-in point, if you've got an even power, because all these even powers look the same, x to the 4th is a parabola, x to the 6th is a parabola, it just kind of sits down on the x-axis harder. Same thing, x to the 3, x to the 5, x to the 7, etc. They're all going to have the same shape, right? So that's why it's useful to know the shape of these graphs, because then you can kind of internally check to see if something's one-to-one. So we know how to prove it mathematically, so we're going to do some of those as an example. But I also want to bring up that, okay, well, if we see something like this, where I've got the same output happening twice for two different values of x, then it's not one-to-one. So I can look at it graphically to determine if a function is one-to-one. So we can also determine if a function is one-to-one graphically. And then I'll put in the horizontal line test. So the horizontal line test, remember the vertical line test was to help us figure out if we had a function or not, right? So we intersected each function and we made sure that we only crossed the graph once, right, for each value of x. So now we're going to do the horizontal line test. So you do these imaginary horizontal lines here. And again, a function is one-to-one if and only if no horizontal line intersects its graph more than once. Right, and so as long as you have this horizontal line and it intersects more than once, it's not one-to-one. Here, you can have as many imaginary horizontal lines as you want, but it's never going to cross the graph more than once. Right, so you can always check your work using Desmos. Sometimes it's easier to just graph it and do the horizontal line test, right? But I expect you to be able to show that something's one-to-one mathematically. So here we go. Okay, so let's do 14 first, nice and easy. So 14, it doesn't say how we should determine if the function is one-to-one, but at least for these simple ones, I am expecting you to show it mathematically and then maybe confirm using Desmos. So f of x is 3x minus 2. So to prove that this is one-to-one mathematically, or maybe it's not, what we do is we set f of a is equal to f of b, right? So remember the little blurb we went to. So we can prove mathematically that a function is one-to-one by setting f of a equals f of b and simplifying. If it simplifies to a equals b, then the function is one-to-one. So I'm going to show you how to do that. So f of a is 3a minus 2 and f of b is 3b minus 2. Now, it looks obvious that a is equal to b, right? Here we started with the simplest one. So of course a is going to be equal to b. Sometimes that's not the case, right? And so sometimes these things are very hard to simplify and then they're probably not one-to-one. So if I want to simplify, I can add 2 to both sides. So I get 3a is 3b minus 2 plus 2, which is going to go away. I also have a is 3b divided by 3, which is also going to cancel out. So now I have a is equal to b. Therefore, f of x is a one-to-one function. So we're going to deal with more complicated one-to-one functions, so I'm going to save it for a little bit. But I do want to look at some of these here. Right, just graphically, we can make sure that x to the 4th plus 5 is not one-to-one. We suspect it's not one-to-one, but I'm just going to confirm it with Desmos. So here I have x to the power of 4 and then plus 5, I think it was. So because I'm able to find two values, hey, where's it? So here at x equals 1, it's 6, and x equals -1, it's also going to be 6. It keeps jumping around. There. Because of that, and also because, oh, tried to use my pointer, I don't have one. Because if I draw horizontal lines across here, I'm going to cross more than once, so it's not a one-to-one function. if we look at, so that was x to the fourth plus 5. That's not a one-to-one function. That's okay, it happens. There are only a few, or not all functions are one-to-one, right? They don't have to be. Here we've got the added restriction, okay, only look at x's between 0 and 2. So now if we go back to our graph, so this is what I meant by, if we go back to our graph, x is between 0, so from here, and then I'm going to try to, well, going all the way up to 2, it's going to be a while until I get to 2. Can zoom out here. It just doesn't like my pencil today. At 2, x equals, oh, still not there. I thought it was there. X equals 2 is when, trying to get it there. So close. 21. Anyways, I give up. So now I'm restricting my window in between x equals 0 and x equals 2 now. Well, I could do the horizontal line test and I would find that it is one-to-one on that range, right? And so it just depends on what area you're looking for, right? What domain you're interested in. Same thing here between t between 0 and 5, I suspect that it's going to be one-to-one on that range. Okay. But, oops. But. So like I said, we're going to do some more complicated one-to-one functions showing that things are one-to-one, because also, like we said, in order to find the inverse of a function, I need to first show that it's one-to-one, and that's where our more complicated one-to-one functions are going to come from. But here you can do these kind of simple things using the horizontal line test. If you have a graph, you can just kind of make sure it's one-to-one or not. Okay, so let's talk about the inverse of a function. So the inverse of a function, just as a heads up, f to the -1 of x is not the same as 1 over f of x, right? Because the -1, the power of -1 is on the f, and so that's how we know that it's the inverse. So let's talk about the inverse of a function. So the inverse of a function, so let f be a one-to-one function. So we've already established here that, okay, we have to have a one-to-one function with domain A and range B. Then its inverse function has the opposite. It has the domain B and range A. And it's defined by, okay, the inverse of y is equal to x and f of x is equal to y for any y and b. I don't know why I sped up there, but for any y in the range of f of x. So here, what we're saying is that, okay, if you apply the inverse to the function, what you should end up with is just x, leading us to the inverse function property, which is going to be really useful. So here, make it bigger. So we haven't found any inverses yet. We're saving that for the very last, right? But here, so let f be a one-to-one function with domain A and range B. That's the same as up here. The inverse function f inverse satisfies the following cancellation properties. So the inverse at the function, right? This is a composition of functions. This is the same as f inverse composed with, oops, I used the same notation they used, composed with f of x, right? So this is just function composition. And then same thing here, f composed with the inverse of x But what these things are, so that's why we had to figure out what function composition looks like, right? And just kind of get a handle on that. Because what we're going to do is we're going to use that in order to show that, okay, well, the inverse that I found is actually the inverse of f of x, because if I take the composition of the two in any order, I'm going to find that I just end up at x. So this is really useful because how it's going to go is I'm going to ask you to find the inverse, and then once you've found the inverse, you're going to confirm that it is the inverse by applying these two function compositions, right? And making sure that you end up at x. Okay, so we use this, we use these two properties after finding the inverse, of f of x, to confirm that the inverse we found is actually the inverse. To confirm that the inverse we found is actually the inverse. Okay. So to start, we have some functions where we're told that, hey, these are inverses of each other. So use the inverse function property to show that f and g are inverses of each other. Well, so now f and g, of course, if g is the inverse of f, then vice versa, right? F is the inverse of g, so they work back and forth like that. And that's what we're seeing here, right? It works both ways. If the inverse of f is equal to x and f of the inverse of f is equal to x, well, they can replace each other because we're checking both ways. So if we have something like, let's do something a little bit, which one did I want to do here? You know what? Because we've already done compositions, let's get straight to 45. So here, what this is saying is that, okay, if f of x is 1 over x minus 1, its inverse is 1 over x plus 1. That looks a little bit different than probably what we want it to be, but that is the inverse of f of x. And vice versa, if we have g of x, then f of x is the inverse of that. So here they're being handed to us. So we're starting small, right? They're being handed to us, and then we're going to make sure that these are the inverses, right? So confirm that f of x is the inverse of g of x and vice versa. So what that means is that show that f composed with g of x is equal to x, and that g composed with f of x is equal to x. Okay. I guess I don't need that question marks on here because I'm stating that that's what I need to show. So here we go. So we're just going to find these function compositions and make sure that they simplify to x. So I've got f of x, or f of g of x, is going to be 1 over g of x minus 1. G of x is 1 over x plus 1. which is 1 over x plus 1 minus 1. Plus 1 minus 1 is going to cancel. So all I'm left with is 1 over x, which is 1 over 1 times x over 1, which is just x, right? And so here, it actually did equal just x, which confirms that g of x is the inverse of f. But we also have to show it the other way. We always have to prove both ways, but this is a good start, right? If we're able to land on x here, we should just as well be able to land on x on the other side too. So if I do g of f of x, g of x is 1 over x plus 1, so 1 over f of x, then plus 1. F of x is 1 over x minus 1, so 1 over x minus 1, and then plus 1. Careful here, you have to have a common denominator before you can add this thing over here. What I'm going to do is I'm going to simplify this a little bit because it's a fraction over a fraction, so I can simplify that. So I get 1 over 1 times x minus 1 over 1, and then plus 1. Hey, it looks pretty good because it looks like I don't need a common denominator. It would have worked out, right? But your common denominator would have to be 1 over x minus 1. So you'd want to try to get out of that and see what you can do. So you get x minus 1 plus 1, which is just x. So it checks out. So now what we can conclude, therefore, f of x and g of x are indeed inverses of each other. Good. Okay. So now I think we're ready to find some one-to-one function, or sorry, the inverses of a function. One-to-one, we already did that. So how can we find the inverse of a function? This is one way that the textbook uses. I use a slightly different way. It ends up being the same thing anyways. I just reverse these two steps a little bit. So another way to find the inverse, just so you know it's coming, but first let's talk about this one, and then I'll give you the other way that you can find the inverse. It's very similar, very, very similar. It's just that you land on the inverse immediately. So first thing you're going to do is you're going to write y equals f of x. Okay, y is equal to f of x, so it's not that big of a stretch. Solve this equation for x in terms of y. Now here's where I don't actually like to do that. So I actually, here, I swap out my x's and y's and then I solve for y. Very similar though, you're going to solve for x in terms of y, and then you're going to interchange x and y. And then the resulting equation is y equals f inverse of x. So another way to solve this is, so you start at the same, right? Y equals f of x. Your second step is to interchange x and y. Your third step is to solve for y, right? Instead of solving for x up here and then switching x and y, all I've done is I've switched x and y first and then I'm solving for y. Solve for y, the resulting equation is y equals f inverse of x. Okay, so let's do an example. I'm just going to chop this off because I want it on this page. So find the inverse function of f. So here, we're supposed to find the inverse. So I already suspect that they're all one-to-one. But what I'm going to do first is I'm going to assume, or sorry, not assume. Let's do 54. 54 is a nice one because it's got x's in both the numerator and denominator, so making it a little bit harder. So first, prove f of x is one-to-one, right? Going back to where we started in this section here, well, and this is 54. F of x is x minus 2 over x plus 2. So remember, I'm going to have f of a is equal to f of b. And I always like to center them, so have my equal sign in the middle of the page. And then I can kind of work around that. So f of a is a minus 2 over a plus 2 is equal to f of b, which is b minus 2 over b plus 2. So how are you going to solve this if you're going to simplify things? Well, first thing I would do is I would multiply my b plus 2 over and my a plus 2 over here to see where I end up at. So I get a minus 2 times b plus 2 is b minus 2 times a plus 2. I'm going to expand this out, and from experience, I know things are going to cancel out. So now I have ab plus 2a minus 2b minus 4 is ab plus 2b minus 2a minus 4. What I like to do, and there are lots of ways that you could go about doing this, I like to shuttle everything over to the left-hand side and see what cancels out, and leaving 0 on the right-hand side. So what I get is ab plus 2a minus 2b minus 4, and in fact, I'm going to ditch that bracket, minus ab plus 2b minus 2a plus 4 equals 0. A lot of this is going to cancel out, right? Minus 4 plus 4, for example, 2a minus 2a minus 2b. Something went wrong. Oh, yeah. What happened? I didn't subtract 2b. How did I muck that up so bad? I did the plus 4. There, I'm going to start over. I don't know what happened. ab plus 2a minus 2b minus 4. Oh, I know. I meant to use brackets and then I decided not to. Minus ab minus 2b plus 2a plus 4 equals 0, right? Moving each individual one over, that's what I missed. But now I can cancel stuff, but not everything's going to cancel. ab minus ab, minus 4 plus 4, and then I've got 2a plus 2a, and then negative 4b minus 4b. So what I get is I get 4a minus 4b equals 0. Well, 4a is equal to 4b then, if I add 4b to both sides. And so a is 4b divided by 4. So a is equal to b. Therefore, f of x is 1-to-1. So we are able to find its inverse. Okay. So we we showed that it's one-to-one, right? So you can use all these as practice for showing that things are one-to-one, and you use the same, and it gets pretty messy, right? But things are going to cancel out, and you're able to show that A equals B. And remember, there are more examples in the notes. I just had to chop them off for keeping them on the page. So if I have to find the inverse of this thing, f of x is x minus 2 over x plus 2. So now find the inverse of f of x is x minus 2 over x plus 2. I'm just going to confirm that that's the one, x minus 2 over x plus 2. Good. All right. Step 1. We said write y equals f of x. So that means y equals x minus 2 over x plus 2. Wait. The next step, I'm going to follow my instructions, right? Because I like to switch out x's and y's and then solve for y. Because what I end up with is y equals something, and I don't have to remember to switch them back. So that's what I like about my way. So the second step is interchange x and y. So where I see a y, I'm going to write x, and where I see an x, I'm going to write y. X is y minus 2 over y plus 2. Then solve for y. The resulting y equals f inverse of x. All right. So now if I have to solve the, wait, it's supposed to be in pointer mode. If I solve this thing for y, right, I slowly have to shift things over. And so I get x is equal to y minus 2 over y plus 2, just writing it again. Solving for y, I'm going to move the y plus 2 over to the right-hand side. So I get x times y plus 2 is y minus 2. Since I'm trying to get y on its own, I'm going to expand this out to try to shake out that y. And so I get xy plus 2x is y minus 2. In one kind of switcheroo motion, I'm going to move the 2x over to the left-hand, or sorry, to the right-hand side, and this y over to the right-hand side. So I get xy minus y is negative 2 minus 2x. I can pull out a common factor of y here, and also a common factor of negative 2 if I prefer out here, which I might do just for practice. Y times x minus 1 is negative 2 times 1 plus x. Right? Expand this just to make sure negative, especially if you're dealing with negatives, right? Negative 2 minus 2x, okay, works out. Xy minus y, I've factored properly. So now I'm able to solve for y if I divide both sides by x minus 1. And so I get y is negative 2 times 1 plus x over x minus 1. So this is the inverse of f of x. This is the inverse of f of x. Therefore, f inverse of x is negative 2 times 1 plus x over x minus 1. So there's a lot of work that we can do around these inverses, right? The next step is we need to confirm that this is the inverse. How do we confirm that it is the inverse? We have to use function composition. So now, next, we need to confirm that this is indeed the inverse right, just like we were doing before, is indeed the inverse by showing f composed with the inverse of f of x is equal to x, and the inverse composed with the function also has to equal x. Because I'm running out of time here, we'll probably only have time to do one, and then I'll let you do the next one on your own, and we'll start with that next day. So let's start with f composed with the inverse of f of x. And so we get f of f inverse of x. F, remember, is, and I'll just copy it here. Copy. I'll just put it here for now, just kind of smaller. And f inverse is this one. Copy. Oops. Keeps, I want it to be smaller. There. So now, if I have, okay, so I'm plugging in the inverse into f of x. So instead of x, I'm going to write f inverse of x minus 2 over the f inverse of x plus 2. Then I'm going to take this step and plug in this function. This is going to get nasty, right? It's going to get really nice and big, but then it's going to slim down, and what we anticipate if we've done things correctly is that an x is just going to fall out. So this becomes, and for the f inverse, negative 2 times 1 plus x over x minus 1. I'm going to put big square brackets around it just to keep them separate for a bit. Divided by negative 2 times 1 plus x over x minus 1 plus 2. In order to simplify this thing, I'm going to end up with a fraction over a fraction, right? But in order to get there, I have to have a common denominator. So what I need to do is I need to times x minus 1 over x minus 1. And then same thing here, x minus 1 over x minus 1. So now I can simplify this a little bit. And so I get negative 2 times 1 plus x minus 2 times x minus 1 all over that common denominator that I forced, x minus 1. Same thing in the denominator. Negative 2 times 1 plus x plus 2 times x minus 1 all over that common denominator of x minus 1. So I can simplify the fraction in the numerator, or both numerators really, the fraction in the numerator and the fraction in the denominator. I can simplify these numerators kind of side by side. So I'm going to expand this out and see if anything cancels out. It usually does. So you get negative 2 minus 2x minus 2x plus 2 over x minus 1 divided by negative 2 minus 2x plus 2x minus 2 over x minus 1. Foreshadowing, right? A fraction over a fraction, it looks like that x minus 1 is going to cancel out, but I'm going to hold it there for a little bit longer. Negative 2 plus 2 goes away, and minus 2x plus 2x goes away. So what I have is I have minus 4x over x minus 1 over minus 4 over x minus 1. All of a sudden, it's very nice and manageable. So this becomes negative 4x over x minus 1. We've got a fraction over a fraction. I have to flip and multiply. So x minus 1 over negative 4 X minus 1 is going to cancel with x minus 1, and the negative 4 is going to cancel with the negative 4. And so, wouldn't you know it, with a minute to spare equals x, right? And so now we would do the same thing, but we need to also show, so we've shown that this is true, so we also need to show that this is true. The f inverse composed with f of x is equal to x, right? So we would do the same thing. It's going to be just as nasty, but you should end up with an x in the end. So I'll leave that for you guys to work through on your own, and we'll start with that next day. Any questions? I'll stop this recording here.